Thanks for watching, and I am Captain Peyamerica. Let me show you another 3 ways of calculating the integral from 0 to pi over 2 of cosine of x. And of course you may say, well, there's gotta be some way of doing it with residues. And in fact there is. So I guess method 1, or even cooler, let's do method 25, because the other ones are on Flammy's video. So let's consider the following function. F of z equals to cosine of z. Complex function, and let's integrate it over the following rectangle. Starting with 0, pi over 2, pi over 2 plus pi over 2i, and pi over 2i. Okay? And then this is part A, B, C, D. Now, first of all, this function, it actually has no singularities. So by, I think, Cauchy's theorem or something, the integral over the whole contour, f of z dz, must be equal to 0. On the other hand, this integral equals to the integral over a plus the integral over b plus the integral over c plus the integral over d. And look, so on the one hand, the integral over a, if you just parameterize the path by gamma t equals to t, it just becomes the integral from 0 to pi over 2 of cosine of t dt. Okay. And what I want to say, so, and let's call this I, because it turns out we'll find an equation involving I. Now, second part. Let's evaluate b. And in this case, b can be parameterized with a path starting from pi over 2 and ending at pi over 2i. And the one that works, it's gamma t equals to pi over 2 plus it, where t goes from 0 to pi over 2. Better not call the IT department because of IT. And this then just becomes the integral from 0 to pi over 2 cosine of pi over 2 plus it, and then gamma prime of t, which just becomes I dt. Now, cosine of pi over 2 plus it, that's cosine of pi over 2 minus it, which becomes sine of minus it, which becomes minus sine of it times I. So that becomes integral from 0 to pi over 2 minus sine of it times I dt. Now, what is sine of it? That's equal to e to the I times it minus e to the minus I times it over 2i, and that's e to the minus t minus e to the t over 2i, and that's precisely I sinh of t. You just multiply top and bottom by I, you get a minus here, which works with this one, so we get I sinh of t. So in the end, you get integral from 0 to pi over 2 minus I times I sinh of t, which becomes sinh of t. And now, although we're not allowed to evaluate cosine or sine, we are allowed to evaluate sinh. So this becomes cosh of t from 0 to pi over 2, which becomes cosh of pi over 2 minus 1. So that was our second integral, the integral over this part. Now, let's do the integral over the top. So let me just cross out this part. So let's see. So, and for c, what we need a path that starts here and goes to pi over 2i. And the path that works here is gamma of t. It's pi over 2 plus I pi over 2. So you start there, and you're just subtracting t because the real part is just decreasing from pi over 2 to 0. And it's still t between 0 and pi over 2. So our integral then becomes integral from 0 to pi over 2 of cosine of pi over 2 minus, let's write it this way, minus t minus I pi over 2. And remember gamma prime, so we also have this minus 1 lurking around. Oh, that reminds me, okay, so since we have time now, my advisor always used to say, it's not lurking around, he would always say, oh, you have this constant looming around. But the funny thing is, in the class I took, there was also a student named Lu Ming. And he was always confused. He was like, why are you calling me this constant? What? It's different. There's looming with 2 O and looming, L-U-M-I-N-G. Anyway, he's doing very well right now. But so, what do we have? So integral from 0 to pi over 2, we have this minus. Cosine of pi minus something is sine of something. So sine of t minus I pi over 2 dt. And let's just expand this out. 0 pi over 2 minus sine of t cosine of minus I pi over 2 minus, because we have plus, so minus cosine of t sine of minus I pi over 2 dt. Now, we can clean this up a little bit. So cosine of minus is the same as cosine of plus. And then sine of minus is the same as minus sine, so plus. And then just like we did with sine of I something, you can do the same thing with cosine of I something. So it turns out cosine of I pi over 2 is just cosh of pi over 2. So we get integral from 0 to pi over 2 minus cosh, so cosh of pi over 2, sine of t, plus, and again remember, sine of I pi over 2 is I sinh, so I sinh of pi over 2, cosine of t, dt. And here's the cool thing. So, if you pull out that constant, you get integral from 0 to pi over 2 of cosine, which is what we want. That's what we called I. And turns out the integral from 0 to pi over 2 of sine, that's also equal to I, just by a substitution. So, we can legitimately assume this. So, this actually becomes minus cosh of pi over 2. I plus I sinh of pi over 2 I, which just becomes minus cosh of pi over 2 plus I sinh of pi over 2 I. So this is what we get from C. And remember, that's what we get from B. And then lastly, we just need to evaluate the integral in D. And it turns out you get something similar. So erase this. So for D, we just need a path that goes down from pi over 2i to 0. So for example, gamma of t is pi over 2i minus it. So the integral just becomes integral from 0 to pi over 2 cosine of pi over 2i minus it, and then minus I dt. And now remember, we have this identity, which I didn't write down, but I stated it. Cosine of it is cosh of t. So this becomes cosine of I times pi over 2 minus t. So it becomes integral from 0 to pi over 2 of cosh of pi over 2 minus t times minus I dt. And then you can just either evaluate it directly or just use a u substitution. U equals to pi over 2 minus t. And you get, in the end, that's equal to the integral from pi over 2 to 0 of cosh of u I dt. Just realize Joshua sounds like Koshua, so cosh u I. Very similar. Anyway, and then you just evaluate it, so it's I times sinh of t from pi over 2 to 0. Sinh of 0 is 0, and so we get minus sinh of pi over 2i. Now this is d. And now we don't need our picture anymore, but we evaluated all the 4 parts, so we need to add them up. And remember, it adds up to 0 because there's no singularity here. So putting everything together, we have a plus b plus c plus d equals to 0. So a was just our integral, I. B was cosh of pi over 2 minus 1. C was minus cosh of pi over 2 plus I sinh of pi over 2. I. And then D was what we just had, minus sinh of pi over 2. I. And we know all this equals 0. And here's a nice thing. Notice how similar those two terms are, right? So cosh of pi over 2 minus sinh of pi over 2i, and it appears here again. So in the end, what we get is, let's just put everything together. So let's factor out I. So I times 1 minus cosh of pi over 2, okay, minus, so plus I sinh of pi over 2 equals, put everything else on the right hand side, 1 minus cosh of pi over 2 plus I sinh of pi over 2. And lo and behold, those two terms are the same, so assuming they're not 0, they cancel out, and ooh, it's groovy, and we get that, in fact, I, which was our integral from 0 to pi over 2 of cosine of t dt equals 1. Woo! So how cool is that? Just using complex analysis. So that was one way, and I promise you the other 2 ways are shorter. So that was a pretty long way. The other 2 ways, actually it's just one way, but like one way with one variation, just uses, again, multivariable calculus. So I've taught vector calculus in the fall, so I got lots of ideas. So let's use the following, and this time let's use sort of independence of path in line integrals. So I guess method 26 now. Consider the following vector field, f equals to 0, 1. Notice this vector field is conservative because if you let f of xy to be y, then the gradient of f, well, that's fx, fy, and that's 0, 1, and that's, that's equal to our vector field f, okay? In particular, because f is a gradient, this is a conservative vector field. In particular, what this implies is that it's independent of path. So in particular, let's evaluate the line integral of this vector field using 2 different ways. And starting at 1, 0 and 0, 1. On the one hand, consider the straight line segment going from 1, 0 to 0, 1. The way you parameterize this is simply, you start at 1, 0, and you end at 0, 1, and you put on and off switches. So, because you want this to be 1 initially, it's 1 minus t, and because you want this to be 0 initially, you put t, and t goes from 0 to 1, and this is just 1 minus t, comma t. So by definition, the line integral of f over this path c1, that's the integral from 0 to 1 of, so f is just 0, 1, so even if you plug in r, that gives you 0, 1, and you dot it with the derivative of r, which is minus 1, 1. That's r prime of t, and that's f of r of t, dt. And if you do that, that's just the integral from 0 to 1 of 1 dt, which is 1. So, on the one hand, the line integral over c1 equals to 1. On the other hand, and maybe let me use some different color, let's evaluate this over a different path, namely, just a unit circle. So let this be c2. Now, the unit circle, you can evaluate it, you can parameterize this just using cosine and sine. So let's do r of t equals to cosine of t, sine of t. From 0 to pi over 2. Then, the line integral over c2 of f dotted with dr, that's the integral from 0 to pi over 2 of 0, comma 1, so f of r of t, dotted with r prime, which is minus sine of t, cosine of t. So that's r prime of t, dt. And that's just the integral from 0 to pi over 2 cosine of t, which a priori, we don't know what that equals to. But we know that the integral over c2 is this integral. But we also know that the line integral is independent of path. So it doesn't matter which path we take. In particular, that integral equals to the line integral of c1 of f dotted with dr. But we've calculated this at the beginning. We found that this is 1. So in the end, the integral from 0 to pi over 2 of cosine of t is 1. That was method 26, using the fact that conservative vector fields are independent of path. And method 27, it's essentially the same, but look, since we found sort of the potential f, we can just use the fundamental theorems for line integrals, which tells us that tells us the following. So again, let's evaluate the line integral of f over the circular path. On the one hand, we calculated the line integral. We just did it. We calculated that to be the integral from 0 to pi over 2 of cosine of t dt. But also, now let's use the FTC of line integrals. The line integral of f dotted with dr is the line integral of gradient of f dotted with dr, which is just f of the endpoint minus f at the starting point, which is f of 0, 1 minus f of 1, 0. But what is f? F is just y, and therefore y is just 1, and minus 0, 1 minus 0, which is 1. So yet again, we found that the integral from 0 to pi over 2 of cosine of t, which is this, which equals this, equals 1. So that's the 27th method of calculating this. Lastly, not the 28th method, unfortunately, but there was another way I figured out to calculate this, but unfortunately it's not quite cosine x, but cosine squared of x. but I still want to mention it. It's a bit circular reasoning, but kind of cool because, so I guess let's call it method 29, was that? Yeah, 28. Gotta be perfect because it's method 28. So what do we have? So it doesn't calculate cosine x, it calculates cosine squared of x from 0 to pi, and also by circular reasoning somehow. Because what is cosine of x? Notice you can expand this as a cosine series. So it's 0 times 1 plus 1 times cosine x plus 0 times cosine squared x plus dot dot dot. Okay, well, I forgot what I was trying to get at. Yeah, sorry, not cosine squared x, it's cosine 2x plus 0 cosine 3x plus dot dot dot. So you can expand cosine out as a trivial cosine series. Right? So this is Fourier series, but just with cosines. And then there's a formula for a Fourier cosine series that just says this coefficient 1 is just the integral from 0 to pi over pi with a factor of 2 because we have cosine series. So 2 times integral from 0 to pi of this dotted with this, which is cosine of x times cosine of x, which is just 2 over pi times the integral from 0 to pi of cosine squared x. It's probably time for me to stop. So 1 equals to 2 over pi times the integral of cosine squared x, and therefore solving this, we get integral from 0 to pi cosine squared x dx equals to pi over 2. Which is, again, a way of not getting cosine of x, but cosine squared x from 0 to pi, and again, using circular reasoning, because to get this factor of pi, it would be the integral from minus pi to pi of cosine squared x. So it's a bit cheating, but I thought it's too cool not to teach, okay? Just as I usually say. All right, so I hope you like this great, sequel to the, MathVentures movie, but just with Captain Peyamerica. And if you want to see more math and more fun, please make sure to subscribe to my channel. Thank you very much.